So this is the goals for us, be able to understand the study design, and I am a biostatistician, but we need to learn epidemiology before we talk about statistics. So first sessions, and I will introduce you to epi concept, i.e. study design. Okay? And then next, be able to understand statistical concept in a medical paper. And then the last, be able to perform a data analysis. So we will talk about how to select the biostatistics test, and then also you will be conducting t-test, chi-square, correlation coefficient, linear regression, logistic regression with your hands on your laptop. Okay. All right, so this is the first part. Be able to understand the study design, and we have only probably 1 hour to cover this, so it'll be very basic concept, but this is probably most stuff and you need to know. And so we will be covering what's the difference between randomized clinical trials and observational studies, and cohort study, case control study, and cross-sectional study. And then second, be able to understand statistical concept in the medical paper. So I'll be introducing you this morning concept of p-value, and what is the difference in mean and median, and what's the difference between standard deviation, interquartile range, and what is the difference between standard error and confidence interval, how to use them. Okay. And then the next, when and how to select statistical test. Test we are going to cover student t-test, comparing two independent means, and non-parametric tests corresponding to it, or paired t-test comparing two paired means, and non-parametric test corresponding to that, and Pearson chi-square test, Fisher's exact test, Pearson correlation coefficient, Spearman's rank correlation, and ANOVA and Friedman test. There are a lot. But I'm hoping to cover this, at least how to select this part in this morning. Okay? And in the afternoon, we're going to use a Titanic data set to conduct all of these tests. And they're exciting. And then the sessions after today will focus regressions. And then I haven't forgotten power analysis. So the very last lecture, I will show you how to compute the power in sample size for your study using a freely available software developed at the Vanderbilt called the PS software. Okay, so this is another software I want you to download. So if you type Vanderbilt in large capital letter PS, and you will find the site, and you can download the PS. Okay. But this won't be happening until Thursday. So when you read a paper, okay, you might think information is so much, and you can't really read them very quickly. Okay. So you end up facing so many papers and then take hours and hours to go through those. But if you know PICO, and this will help you to skim through those papers very quickly, and then help you to understand and what is a study, what is a study design. Study design is very important for you to understand quality of their research or their analysis. Okay, so let's start with the PICO. What is a P? And P is P for population. Who are they? Who are the subject? Who are the subject? And E is exposure. Okay, what is the risk factor they are studying for? And then what is intervention if they intervene patient? And what is the exposure of interest? Those are the same word. I might use it interchangeably. Okay? And what is a control group? And okay, what is a comparison? And then last, what is the outcome? So this is a paper in looking about effect of aspirin use on the patient mortality. Okay, so this is the abstract, and you see, and then first, and let's see what is a PICO. P for PICO, P, population. Who did they study? Okay, so let's read patients. And 6,174 consecutive adults undergoing stress echocardiography for evaluation of a known or suspected coronary disease. Okay. So these are the patients who showed up at the Cleveland Clinic, and then who took an echo and for suspected the coronary disease. Okay, that's the population. Okay, so that's a P. And what is exposure of interest? What are they studying? And aspirin. Okay, so at the baseline, and then they divided patients into two groups. One used aspirin when they showed up for echo. Okay, that's the baseline. Who used the aspirin? That's the exposure E. Okay, and then what is a comparison group? So they graph patients and who showed up for echo but did not use aspirin. So that's the control group. Okay, and then what is the outcome? Outcome is a long-term mortality. So they followed up patient median of 3.1 years and max of 8 years, and to observe their mortality or their survival. Okay, so death is the outcome. All right, so this is a PICO, and then now we can talk about the study design. Okay, so without knowing this PICO, it's really hard to understand what the design they use and what type of analysis we should be doing. So always, whenever you grab a clinical paper or any quantitative papers in clinical research, 4 letters. Okay, it's very important. And then switch to the next topic. And so now we are going to classify studies into study designs. Okay, we now classify study design. And mainly we can divide the study design into 2. Experimental studies and observational study. So what is an experiment? Experiment, we can call it intervention, right? So you have a patient in front of you. So if you intervene them with some treatment, and purpose of your intervention is your academic curiosity, scientific curiosity, and then you intervene patient, and that's what we call experiment. Okay. And you might give a treatment to patient for the patient. That's a healthcare. That's a treatment. Okay. But if your purpose is to satisfy your academic curiosity, okay, your research question, not really serving to care patient, right? You give a treatment for your research. That is an intervention. So that's how we differentiate routine care of a patient and intervention, i.e. research. Okay. To care patient, you don't need IRB approval. But to do intervention, okay, you might give the same treatment anyway to the same patient, but the purpose is different. If you do it for your research, you need IRB approval. Okay? So those are experimental study. And then experimental studies, and it can be randomized and can be non-randomized. So if you flip a coin to decide, you don't really flip a coin, but we usually use computer random number generators to know which one, randomly assign which patient get the treatment, which patient don't get the treatment, and we call it randomized controlled trial, RCT. Okay? And experimental study doesn't have to be randomized always. So you grab a Vanderbilt, and then all of the Vanderbilt patient get the new drug, and then you grab the Baptist patient, and then they get controlled drug. Okay, that's again, it's still experiments, but there's no randomization. Okay. And then we have observational studies. Observational study, there is no intervention. So what you do is you are purely observer, okay? And then you just observe and record what's happening to each patient. Then that's an observational study. In observational studies, and mainly we have 3 different types. 1, cross-sectional study, and 2nd, cohort study, and then 3rd, case control studies. And I'm going to explain one by one. And most observational studies, even experimental studies, you should be able to classify into these 3. Because randomized controlled trials, actually, this is under cohort study. So almost any studies, epidemiological study, quantitative studies, have to be classified into these 3. If you don't, then you have to think of study design. I've seen some weird studies. I can't classify. There must be something wrong in there. So I start digging. But anyway, hopefully you can classify the studies you've known into these 3. Okay. criteria for study design. There are two things I want you to pay attention to when you classify study into these study designs. Okay, one, method of sampling. Okay. So sample data or census data. So what is the census data? Census data is data systematically collected on every patient in a group, i.e. a cohort of a patient. So you identify a group of patient or group of people, and then you measure every single one in the defined cohort. Okay, so that's what we call census data. And what is the sample data? Sample data, and you may identify cohort or you may not identify cohort, but you randomly pick patient who participate into your study. Okay, it's a simple, right? So you define a cohort and grab everybody in the cohort, that's the census data. Or you just randomly pick from the defined cohort, or sometimes undefined cohort. Okay, and then the next one, timing of data collection. Okay, timing of data collections is mainly divided into two parts. One, like a survey, you collect the data at the moment of time. Okay, so that's one. Or you follow a patient over time and then made several assessment. Okay, so is there follow-up or there is no follow-up? Okay. So if you know these two, and you should be able to identify study design. So it's as simple as that. It's not hard at all. Okay. So so let's start with one by one. And this, we will come back to this slide, but cohort study, okay, and can be classified into two, prospective or retrospective cohort. Okay? And case control study can be prospective or retrospective. Okay. So what? And then we have a cross-sectional study. So okay. So I know it's still confusing, and then let me explain it one by one. So let's start with the cross-sectional study. In cross-sectional study, okay, and this one is a study like a survey, and you collect the data at a moment of time. Okay, so there is no follow-up. It's like you taking a snapshot, right? So that's defined cross-sectional study. Okay. So what can you see from a cross-sectional study? So you want informations and how much of population in Nashville, for example, have cancer. Okay? And you might send out a survey for everyone who are over, let's say, age of 50, and then ask them, do you have a cancer? It's kind of that questions, but do you have a lung cancer if you have a specific type of cancer of interest? And then you, at the same time, ask, at the same time, do you smoke? Okay, so you can get some idea how many people in Nashville have a lung cancer and smoke. All right, so this has nothing to do with sampling method. You might send your survey to everybody who are over 50 years of age in Nashville, or you randomly pick from people who are age over 50 in Nashville and send a survey. It doesn't matter. And so what matters for cross-sectional design is just one thing. Okay, here, timing of data collections, whether you collect data just one moment of time or not. Okay, so that's defined cross-sectional study. All right, cross-sectional study is efficient, right? Because it's easy to send a survey. If you guys are so lucky you have access to RedCap. You think I'm spending like so much time to be able to use a RedCap. But anyway, we had to buy server, we had to hire IT and start all over from scratch. But anyway, the red tab have a nice portions for you to automatically do survey. Okay, create a survey on the red tab, send the email link to everyone, and then you can collect the data automatically, and red tab will do the frequency table and the bar graphs automatically. It's very easy. So it's efficient, it's very easy, but this is the weakest type of a study design. Okay. And because it's often biased for questions involving time between exposure and outcome. So 30% of people smoke in Nashville, and then let's say 10% people have a lung cancer. That's too much, but anyway. But some of the people who don't smoke might be not smoking at the concept of they have a lung cancer. Right? So they stop smoking after they're diagnosed with lung cancer. And so we can't really identify objectively the timing, whether the smoking happened before lung cancer. Okay, so the timing is a gold standard concept in epidemiology. So you have to make sure exposure happened before disease happened. Okay, so you might think it's okay if we ask, did you smoke before you're diagnosed with the cancer? And you might think it's okay, but we don't see that as objective enough, right? Because what is the incubation time for cancer? And how do you know the smoking happened really before the person developed cancer biologically? Okay, so the survey is weak. However, the way you ask, as long as it has a nature of survey, and we have to consider it as a cross-sectional design, and the weakness of cross-sectional design, we can't really identify exposure happened before the outcome. All right. And without cross-sectional study is good. I have one paper published in New England Journal of Medicine based on the cross-sectional design. Isn't it great? So the patients, what we did is we collected data with the patient with the lupus. So, and then we identify healthy control from a database of CRC at the Vanderbilt. Okay, and then we invited them to come to a clinic one day at the Vanderbilt, and then we drew blood. Okay. And with the blood, we identify who have a coronary calcifications and who didn't. And we measure a degree of a coronary calcification, and then goodbye. So patient came into clinic just one day. Okay, so we took a snapshot of what's happening to those patients at one day, and we asked them a bunch of survey questions. Did you smoke? And what is your weight and height, and many things. Okay. And then we actually did get the publication. So it's considered a weaker kind of study, but sometimes very effective. Okay, so this is a paper. All right, so next we are done with cross-sectional study. So next is a cohort study. So what is a cohort study? We define cohort. So this cohort means like a census data. We define a cohort, i.e. group of patients. It could be based on patient characteristic. It could be based on some timing, calendar time. It could be based on anything. But anyway, you define a group of patients, and then you follow them over time. So keyword, follow-up. Okay? So define a cohort. And then the cohort study, and we follow up to see who developed outcome. Okay. So first thing you have to make sure, okay, and people have to be free of outcome. Okay. And because if they already have outcome at the baseline, that means they reached outcome already. So they are no longer at the risk to develop the outcome, right? So therefore you don't follow them. So at the time zero, you need to know who are at the risk for disease. That means who do not have a disease. And then follow them over time, and then see who developed the disease. Right? And then typically, and then you document many things at the baseline. And then because you know for sure those are happening before the outcome, right? Because at the baseline, they are free of outcome. Okay, so you know for sure the factors you collect at the baseline are preceding an outcome, happening before the outcome. So that satisfies the gold standard of epidemiology. Exposure comes before the outcome, right? Okay, so the cohort study, i.e. follow-up study, can be classified into two types. And this one is according to whether the data you're going to collect already existing at the start of the study, or it doesn't exist, therefore you're going to collect. So let's say you have a rich data in the Vanderbilt medical record system. Okay, it's all are in electric, like synthetic derivatives. Okay, and then I say I'm interested in learning whether the smoking is a cause of lung cancer, and then I have a pool of 10-year worth of data from a Vanderbilt outpatient. So that means when you are starting your study, data are already collected in the electric form, or could be in the paper form. You just have to retrieve those data, and then that defines retrospective nature of a study. So you call it retrospective cohort study. Yeah. And then to contrast to that, and so you might be starting study now, and then you might not have any data collected. So you are spending next 5 years to collect those data, and then we define this as a prospective nature of a study. So we call it prospective cohort. Okay. So let me clarify. Okay. So what defines cohort? So definition of cohort have nothing to do with this retrospective or prospective component, right? So the definition of cohort, whether you define patient today or 10 years ago, you define a group of patients based on some characteristic. So characteristic could be the patient who came to Vanderbilt outpatient clinic. Okay. If it's today, and that means that's a baseline, and you will be following them up over time. So that would be prospective cohort. If it's 10 years ago, okay, you define cohort as a patient who came to Vanderbilt outpatient clinic 10 years ago. Okay, so that defines cohort, and then data are already there. So that's defined retrospective cohort. All right, and then the next. So then what is the so we will contrast this with a case control study. Let's see. All right, so let's wait on case control study then. So let's talk more on the cohort study. And what is the advantage of a cohort study? In a cohort study, and as you define patients based on, you could define patient based on exposure. So for example, if you know patient with lupus is very rare, right? So we can't really grab entire population of Nashville. That's not efficient. So how we grab a patient? We first grab everybody with lupus today, for example. Okay. And then that's a cohort you define. And then you could define similar number of patients without the lupus. Okay, you define cohort. But then everybody in your cohort you follow over time. Okay, so that's a cohort study. So it works with a rare exposure. If exposure is rare, you can grab everybody with the exposure and follow them over time. Okay? And then since you are collecting data over time, especially with a prospective study, and you can capture multiple diseases, you are not limited to capture only lung cancer. Like Framingham study, which is more than 30 years of prospective cohort study, and they capture many things, right? Like heart disease and cancers, many forms of cancers. You know, we are following them over time, so why don't we collect data on other disease? So you can do that. And then since, so the third, since you know at the baseline, no one has an outcome, so you know for sure exposure information you collect on the baseline is happening before the outcome. Right, so that satisfies the gold standard concept in epidemiology. And then the 4, less sensitive for selection bias, since you grab everybody and then you follow. I mean, you don't grab everybody, but anyway, you define a group of patients, and then within the group, within a cohort, you follow everybody over time. And so you are not selectively picking patients based on the outcome. Okay? And so you are less vulnerable for selection bias. And the last one, if this is particularly when you're doing prospective cohort study, and since you are collecting data for your research, and so you probably have a design set up so you avoid information bias. Okay. So for example, the people who measure outcome, and you can make sure that they are blinded for exposure status. Okay. So that way you can avoid the patient who are measuring outcomes or selectively judging whether a patient have outcome or not based on exposure. So you could have a better design to avoid information bias if you're doing prospective cohort study. Retrospective is kind of hard. It's a cohort study, but many retrospective data are not collected for research purpose. So you might still have a selection bias, you might still have an information bias. Okay. So the last 2 are more for prospective cohort study. Okay. And disadvantage of a cohort study, and so this is again for prospective cohort study, since you are collecting data over time, so it may be costly and then it may be time consuming, especially for rare disease. Okay. And if it's cohort, let's say loss of subject, due to migrations and death and etc. So even when you have a perfectly designed study, and since we are following humans, so sometimes a missing observation occur. But prospective cohort design is much, much better than retrospective cohort design in terms of a missing. Okay. And so I think, prospective cohort study is still a stronger design for missing patterns. Okay, and and then the last one, as I say, rare disease. If the outcome is rare, it takes a long, long time to collect enough sample size. So it might not be good for rare disease. So what is good for the rare disease then? Case control study. Okay. So I come back to the slide I skipped. But anyway, let's talk about case control study. So let's see, you have a blood sample, okay, for 10,000 patients, and who came to Vanderbilt outpatient clinic last 5 years. And then you have a blood of them sitting in the refrigerator. Okay. So if you use all 10,000 sample, then that could be a cohort study. Right? But think about it. Can you use all 10,000 patients' blood? So what do you want to do? You want to measure biomarker? How much to measure, for example, a CRP or NGAL or gene, one SNP, or entire genome? How expensive? So let's say it takes $100 to run one person's blood to do one test, and that's the exposure, because I'm interested in if the marker is relating to a cancer. Okay, all right. And then how much do you have? Okay, marker information. So we can't just grab blood. We have to run some tests to collect data, right? So you got, let's say, K award. How much your K award provide? $100,000. That's too much for K award, maybe. $50,000, let's say. And after you take out your salary, maybe $10,000 left. to run the assay. Okay, 10,000, and then one sample costs $100. So that means you can only run 100 assays, right? So that's your budget. The budget already determines sample size. So then, who should we pick? Which 100 patient we pick from a research? The research is holding 10,000 patient blood. Okay? And I want to study, say, lung cancer. Okay? So should we grab everybody with lung cancer first? Probably yes, right? Because rate of cancer, let's say if it's only 1 out of 1,000. So if you randomly pick from these 10,000 patients and you only end up, you might not be ending up with any cancer patient, right? So then you can analyze this data. So why don't we look at the data? Because we already know who have a cancer, because we can merge their blood ID with a medical record. Okay, so let's grab first, if it's 10% and 10,000, we have 100 patients, but our budget is 100, so we do need a control group. So let's just grab 50 cancer patient blood, okay? And then in the research, and another 50 have a cancer, so we have 99,900 patients without the cancer, right? So let's randomly pick 50 out of those. So we end up 50 cancer patient blood and then 50 non-cancer patient blood. Okay, and then finally we run assay, and then we have a biomarker or gene data for these 100 patients. So this study is called a case control study. Okay, so what defines a case control study is when you select who to study, you need to know who have a disease, who have an outcome, right? So if your analysis is looking at outcome of death, then you have to know who died, okay? And then grab those people first, right? And then after you identify those with the outcome, and you go back to the research and randomly pick one from patient without outcome. Okay. All right. So the difference between case control study and cohort study, in the cohort study you define a population, grab everybody, and then you need to use everybody's data in analysis. In contrast to that, you randomly pick from a group of patients and based on the study outcome. So the analysis become very effective. Why is effective? With 100 patients, when you have 50-50 outcome and non-outcome, okay, and then statistical tests provide the best power, okay, to detect what you're studying. Right? So what is statistical power? That's the ability for you to detect the signal when there is actually signal. Right? So even if you have 100 patients, but only 10 has an outcome, 90 did not have an outcome, and the power is not as big as where you have 50 outcome and 50 non-outcome patients. Okay, so based on that, case control study is statistically very, very efficient design. Okay. Right, so that has that become popular for that reason historically. Okay. Right. There's a difficulty. It's efficient designs, okay, but there is a difficulty in the case control study, and which one? Okay. Right. We talk in the disadvantage. Okay. Advantage, as I say repeatedly, it's efficient statistically because we have the same number of events and non-events. And then it works with rare events, right? So we have 10,000 patients' blood in the research, and we know cancer is very rare, so we cannot blindly pick samples. So we focus on cancer patient sample to start picking. So it works with rare disease. Okay. And yeah. And then third, In case control study, you would pick when you know for sure you can't run assay on every single patient in a cohort. So if you're rich and then you can run assay on all 10,000 patients, do it. That's give you cohort study, okay, not the case control study. Okay, you do case control study only when your resource is limited. Therefore, you can't collect information on exposure for every single patient. Okay. Right. So when I work as a biostatistician at the Vanderbilt the last 14 years, and sometimes I encounter these people, and I want to conduct the case control study. Yeah, because I know for sure reviewer want me to do case control study. Yeah, and then I'm studying whether the smoking is kind of not a great example. It's not exciting. Whereas use of a drug, let's say, use of a steroid is causing some cognitive issues. Okay, that's something I want to study. And I say, well, how many samples do you have in your record? You're doing retrospective study, right? So you already have a data. So how many do you have? And I have about 1,000 patients in my record. It's already in a diskette I brought for you today. Okay, and then why you are doing case control study? Is it? Well, I thought I need to have the same number of cases in control. It's not quite, because you know for sure all the data is in diskette, right? And then we can analyze your data now, right? So that means you have every single information necessary for your study. So why do we have to select a small portion of subjects? Why don't we use everybody in your diskette? And then he said, oh, can I? I said, of course you can. I mean, the more sample size, and that'll give you more power. So he said, okay then, right? So let's do it. So it's not the case control study. No, it's not. It's a cohort study. So do you see? So only reason you do case control study is you still have to collect data, mainly on the exposure, right? And then you are going to run outside. You don't have a resource. You don't have money. Therefore, you have to shrink sample size to match with your budget. And if you can't measure everybody who to measure most effectively, grab everybody with the cases with the outcome first. Doesn't have to be everybody. If you can do only 50, that's fine. But then match people with that disease. Okay, and then you measure assay. Yeah. So that's the only case you do case control study.
So how about power comparison between case control and total?
Cohort study? Okay. So let's say if you have a 10,000 in your diskette, right? And then only 100 have a disease. Okay, rest of it non-disease, right? So let's compare that with a scenario. You can do case control study, and then you can afford a 200 patient. That means 100 cases, 100 control, right? And cohort, of course, will give you more power because N is 10,000, and then same number of cases, right? But the case control, N become 200, and 100 cases and 100 control. So statistically, you have a bigger power when the total number of subjects is bigger. And that clear? So in this case, yeah, another example, right? You have 1,000 patients, and only 50 have a disease outcome. Okay. So you have everybody, all the data is in your diskette, so you can do cohort study. Okay, so you can compute power. And you limit intentionally to 50 cases and 50 control. So N become 100. So here, okay, N for disease is 50, and total N is 100. And here, N for disease is 50, total number is 1,000. So this has more power. Okay. But situation could be tricky if you have 50 event, 1,000 patients total N, and 30 events and 30 control. No, 50. No, that case is clear. You okay? What did I confuse? Yeah. How about 50 events in 1,000 n, and then here, yeah, 50 and 50. This has more power, right? Okay, okay. But when you have 100 and 100 here, I'm not sure. We have to run power calculation. Yeah.
What about if the cohort also is 100?
Cohort is also 100? Yeah.
50,
And it's 15. Yeah. So in this case, I usually compare, you only have this cohort. That's the only data you have access to. So your option is really you run 15 and 85, 15 events, 85 non-events, and you have only 100, right? So that's the data you have access to.
No, I meant 50 with disease
Right.
and only 100 patients. And then with the other study, the case control also 50 control and 50 experiment.
So case control you have 50 and 50, and then cohort you have 15 and 85.
Oh, 50 and 50.
Oh, 50 and 50.
Which has more power.
And, okay. Then the statistics probably, the power is the same. Yeah, it's the same. Yeah. Statistical power doesn't really go with the study design. So as long as you have the same exposure, same number of exposure, same number of outcome. One is cohort, one is case control. It doesn't change result of statistical analysis. Yeah. Okay. But typical scenario is, you have a cohort already identified, right? Yeah. So the cohort study is you have fixed n. And what you're facing is when you do case control study, n for events is less than what you already have in cohort, or could be the same. Right? So in that case, typical scenario when you do cohort, when you do case control, n is same or less with the case control, right? So the power is more if you grab everybody in a fridge in a cohort study, right? So if you don't have to collect data and don't even think of a case control study, there's no reason to do it. So the case control study disadvantage, since we sample on the outcome, so we can study only one outcome. Okay. So if you have two outcomes, and then you have to randomly sample two sets, and which become much harder. And the rare exposure is hard. So if you know radon exposure is very little, then you might think of cohort study. That means you focus grabbing patients if they have a radon exposure. Okay. And then follow them over time, or do the retrospective cohort study on the radon exposure. Okay. And then a big disadvantage in case control study, we can't really compute the risk. And I'll show you example later for that. And CI means the cumulative incidence probability, and IE risk. So we can't estimate what is the percent of a patient who develop a lung cancer if you're doing a case control study. Because you have 50% lung cancer, another 50% non-lung cancer. That doesn't mean the risk is 50%. You're the one who decide 50-50, right? So it shouldn't change the risk of a cancer. Right? And more sensitive to selection bias. So the biggest disadvantage in case control study is since you're the privilege of choosing control. And so if you grab a wrong control, then you have a wrong result. So who you choose as a control is very important, the case control study. And in contrast to that, in cohort study, since you grab everybody based on exposure or based on something else, and you follow them, every single one of them over time, so you don't have to worry about much of selection bias. Okay. And more sensitive to information bias. For example, if you identify mother with childbirth defect, and then identify the mother with the healthy babies. And then if you ask mother, what did you do during your pregnancy? And then mother with a defective child might remember more. But that's something they may be thinking every day compared to the mother with a healthy baby. Okay, so next two slide give you the example, actual number example to contrast cohort study and a case control study. Okay. So cohort study, this is the data from Framingham cohort study. In Framingham cohort study, and then they identified 8,000 patients. Okay, and then at the baseline of starting over 30-something years of follow-up, they identified patients who smoked at baseline, that's 3,000, and then who did not smoke, and those are 5,000. And then they followed them over time and for 30-something years, and then they collected data and who had a coronary heart disease. So 171 patients did have a coronary heart disease, and then rest of it did not have a coronary heart disease. So compute the cumulative incidence, i.e. risk. Okay, what you do is you divide here. Among three, you divide 84 divided by 3,000. So this really probability of having CHD among smokers, which is 2.8%. And you do same thing for non-smokers, and then which give you 1.74% of a risk of CHD among non-smokers. And then in order to compute the relative risk, what you do is you simply divide probability of having CHD among smoker by probability of having CHD among non-smoker. Okay, so that gives 1.61. So this is a relative risk or risk ratio. We call it RR. Okay? So if you see RR in medical literature, that's this one. Okay? So 1.61 means if you think the risk of having CHD among non-smokers is 1, and smokers have 1.61 risk. That means 60. If you smoke, it's 61% more risk of having a heart disease with smoking. Or smoking increase risk of CHD by 61%. Okay. So that's how you explain relative risk. So in a cohort study, since you're starting with exposure and then you count how many develop outcome, so you can compute risk. Right? In contrast to that, if you have a case control study, okay, and so this one outcome is a prostate cancer, and then so you have 100 patients with a prostate cancer and 100 patients with non-prostate cancer, and then you can't really say, as I said before, 50% chance of having prostate cancer. Right? So if you do 100 and 200, 1-to-2 ratio, you have more budget, therefore you just increase number of control. That doesn't mean the risk of having prostate cancer becomes 33%. Yeah. So case control study, you can't really compute risk anymore. So what you do is instead you compute odds. Okay? So let's talk about odds ratio. So before we dig into this table, and let me explain you what is the odds. Okay. So odds are developed or used often among gamblers. It's not used much among medical workers. I think we are more used to talking about probability, right? And risk is the same as probability. Okay. Proportion, same as probability. So we used to proportion and probability more than odds. But anyway, let's pretend that we are gamblers and we went to Las Vegas, all right? So I did 4 blackjacks. Okay. Statistician only play blackjacks. Right? Because winning always is the best with the blackjack. 50 and 50. Anyway. So I did the 4 blackjacks and I won 2 and I lost 2. All right. So what is your name?
Andrew.
Andrew. Okay. Andrew came with me to Las Vegas and then he played 4 and won 3 and then lost 1. Okay. So let's compute probability of me winning blackjack. 2 and 2. 50%, right? Andrew. 1 and 3. 75% winning, right? Chance of winning. And so what is our relative risk? I have a hypothesis. Andrew is better than me. Or, I wanted to say I'm better than him, but, and so what is the relative risk in our case? 75 divided by 50. So our relative risk is 25, 75 divided by 50. 1.5, yeah, 1.5. So I can say Andrews have 50% better chance of winning than me. Is that correct statement? Yeah. So you say that if you are doctors or if you are medical workers. But if you're a gambler, you don't say that. Probability, it doesn't sound fancy. All right? I want to talk about odds. So what is my odds of winning? 2 and 2, 2 to 2. 1, right? 2 to 2, number winning, number losing, just press your dot. So 2 to 2 is 1. My winning odds is 1. What is Andrew's odds of winning? 3 to 1, 3 to 1. 3. 3 is odds of winning, 3. So what is our odds ratio? 3. Yeah. So odds ratio in this case is 3. And based on odds ratio, can I say is 3 times better chance of winning? No, only 50%, right? Right? Okay, I have 50% chance of winning, right? That doesn't mean he had 150% chance of winning. So he had only 75% chance of winning. That means 50% more than me, not 3 times bigger than me. Right? So be careful when you start talking about chance, talking about risk, using odds ratio, and you make a mistake. Right? Odds ratios are always more than relative risk. It exaggerates association if you start using odds ratio as increasing chance, increasing risk. So be careful. But in terms of odds, let me make it clear. Okay? When you have a positive association, odds ratio is always bigger than relative risk. When you have a negative association, odds ratio is always smaller than relative risk. That means odds ratio is always more toward away from the norm. So if you have intervention decrease chance of death by 25% by relative risk, that means your relative risk will be 0.75. And odds ratio in this case will be smaller than that. So that might indicate odds ratio is 0.6 or 0.5. So 1 is ratio, so 1 means nothing, no difference. So if it's less than 1, odds ratio is always less than relative risk. If it's greater than 1, odds ratio is always greater than relative risk. So I don't want to confuse you, but anyway, odds ratio is always exaggerate other numbers you would get lose. So be careful. But as long as you use the words of odds, it's okay. So if I say Andrews have 3 times better odds of winning than me, that's a correct statement. Okay. So you just can't talk about risk, can't talk about chance, can't talk about likelihood if you have odds ratio, but you can talk about odds. So in the literature, when you have odds ratio is more popular. Why? Software limitation.
Or, I don't want to mislead you, but you could use the word chance or risk, but you can't just interpret number of odds ratio as risk, as chance. So you can say smoking, the odds ratio is 2, and that is statistically significant because p-value is less than 0.05. So it seems smoking is increasing risk of lung cancer. And then parentheses, odds ratio equal to. Then that's okay. Because you're not trying to say 2 times more risk. Okay, if you smoke. You know what I mean? So just never try to interpret the value of odds ratio as you have a risk. Okay. Yes.
So how do you decide when to use the risk and when to use the other risk? So is the risk you associated with the cohort and the other risk associated with the case?
Yeah. So historically, odds ratios are developed for case control studies because you can't compute the root of risk. So you need some other measurements. So that's the odds ratio. Okay. So in this case, we know we can't talk about risk, so instead, and we compute odds ratio. So case control study, and since you are starting with cases, right? So what we compare is between cases and non-cases, and we compare odds of having exposure. So if the cases have more odds of having exposure, and then you might have evidence and says exposure lead to outcome. So what is the odds of smoking within prostate cancer patient? 49 to 51. That means 49 divided by 51. So that's the odds of smoking among cancer. And then do the same thing. Okay. And the odds of smoking among non-cancer, that's 33 to 63. So 37, 37 divided by 63. And so that's the odds. And then take a ratio of the two, and then that become odds ratio. So, isn't it amazing? This odds ratio is actually very close to rate of risk you have on the previous cohort data. Actually, I changed this label to prostate cancer, but this actually should be the same thing because I generated this 2x2 table, which by consuming same probability from the previous table. Okay, and so this 2x2 table is constructed based on the previous cohort study. If you use odds ratio and odds ratio become very similar to the rate of risk, you would have gotten from a cohort study. So this is a historical background. So that in text of epidemiology text, and they say use odds ratio for case control, but use a rate of risk for cohort study. But reality doesn't work that way. With the software limitation, not many software do rate of risk, so therefore almost only choice we have for binary outcome variable is odds ratio. So when you have cohort study, RCT is a form of cohort study. And we do odds ratio almost all the time. So answer to the questions I had. Historically, we should be using odds ratio only for case control, but that's not true. Odds ratio is used for everything. So that's why we have to be very careful. So when odds ratio becomes very similar to rate of risk, when disease is very rare. So mathematically, odds ratio mimics rate of risk when disease outcome is rare, which is a case for case control study. And although for cohort study is not good for rare disease, rare outcome. But we do use odds ratio for cohort study. What happened? Odds ratio start exaggerating more and more to the rate of risk.
Sorry, can you say that again? So you said that odds ratios approximate relative risk. Can you just phrase that in terms of exposures and outcomes rather than
When the event is rare among non-exposed patient population, odds ratio mimics rate of risk. Okay, so when the outcome is rare among non-exposed patient, right? So let me show you. I think this is very important. So let me show you some numbers.
a second. I have a good spreadsheet I want to show you. All right. So this is a spreadsheet I downloaded from somewhere for a long time ago. So let's say if the odds ratio of 2 in control risk, so this is event rate, prevalence of event among control, among non-exposed. All right. So if you're comparing lung cancer probability between smokers and non-smokers, 0.01 is rate of cancer, lung cancer among non-smoker, right? So in this case, relative risk become 1.98. So odds ratio is very similar to relative risk, right? But if this becomes 0.1, let's see what happens. Okay, odds ratio is 2, but relative risk is 1.8. Right, so let's see if this is 5. Okay, and 1 out of 2 have a disease, very, very common. Right, and relative risk is 1.33. So relative risk, and we can talk about increased risk, right? So if relative risk is 1.33, we can say 33% increase in chance of having cancer if you smoke. But odds ratio is actually 2. So you might mistakenly say twice, chance of having cancer increased twice as much if you smoke. Right? Software give you odds ratio. It won't give you relative risk, unfortunately. Logistic regression give you odds ratio. It does not give you relative risk. Okay, and I worked with when I was at Vanderbilt. I worked with a group of people doing a delirium study in ICU. So one of the paper we published, and we identified a patient who had ApoE4 genes for Alzheimer at the ICU admission. And then we wanted to see whether having ApoE4 gene is increasing risk of having delirium during ICU stay. And the odds ratio from this paper is 10. It's 10. Yeah. And the prevalence of delirium in ICU is among non-ApoE4 people at 0.8%. And then in the conclusion, my collaborator wrote this. Also the chance of having delirium increased by 10 times more if you have ApoE patient. Okay, chance of having delirium increased by 10 times if you have ApoE patient. Come on. All right, you cannot have 800%, right? Without ApoE, we already have 80% patient with delirium. How can we have 800%? Yeah, so I'm gonna delete this. And that was my advice. If you think it's that kind of thing and it's obvious, but people still do make mistakes. Right. So what we say is that there is an association, big association between ApoE4 gene and delirium. Yes, and p-value equal 0.01 something. And the inverse odds ratio equal 10. If odds ratio is greater than 1, that means we know relative risk is greater than 1. So we can talk about increased risk, but just don't try to interpret the number of things. So let's see if this is 10. I was curious. So what was a mistake we were about making in that case? All right? So we could say 22%, but not 800%. I mean, not 1,000, but in this case, 1,000%. And of course, right, if the denominator, when you compute the relative risk, if denominator is 0.8, numerator can go as high as 1, right? So highest you can get is 1 over 0.8, which is close to 1.2. So relative risk is actually have a ceiling effect, and relative risk, maximum of relative risk is already determined by the baseline risk among control group.
because numerator can go up to 1 anyway. The odds ratio can go infinity. So odds ratio moves from 0 to positive infinity. So odds ratio does not have a ceiling effect. So therefore, mathematically, odds ratio is actually better measurements. When we do regressions, many times odds ratio, many times risk regression fail because of a ceiling effect. Mathematically, it's harder to compute, but the odds ratio is more robust. So estimation of p-value is more accurate with the odds ratio, more stable with odds ratio. That's why many software prefer odds ratio regression, which is logistic regression. And we will talk more about that when we do logistic regression. But anyway, be careful with odds ratio.
Is there any example when odds ratio and relative risk are actually equal?
Equal? Similar? Yeah, when the control risk, this means
0.
risk of outcome among control group is smaller. So if we make this to, let's say, 0.1 even. It's not close enough. And how about you make it 0.05? Yeah. Okay. So the smaller with this number, odds ratio and relative risk start matching. So what is the design for rare disease? Case control study. Yeah. Okay. If you really wanted to compute the relative risk and then do regression, please come talk to us. Statistician, we know how to do relative risk regression. But usually people do use logistic regression and just stay with odds ratio. I think this is a good time to